one of two integration techniques, change of variables. There's two derivative rules, chain rule and product. This is the anti-chain. We write down the chain rule and integrate it. Little f is the derivative of capital F, and that's the chain rule. Look at the function structure. For substitution to be successful, it must have this function structure. Little f just has to be a known antiderivative. Little g doesn't have to be a function, it just has to be everything leading up to the thing you know. Let's do an example to illustrate. Inverse sine. 1 over square root 1 minus the square is not a function, but it's a known function. I know its antiderivative is inverse sine. Then for g, just something. How about the exponential? So this would be the breakdown. Remember, doing antiderivatives is a guessing game. You just have to map out the function and see what the structure is and make a guess. There's a method to help put structure to your guess. Change a variable. So you start with mapping the function. Run it through the linear map. Square root, reciprocal, yikes, times the exponential. In terms of the structure though, the bottom link must be g prime if it's going to be a substitution. That means I got to find its antiderivative on the upper link. It's right there. That's got to be g. Everything past it then must be f. I look at that function. I don't know that antiderivative. It's not on my little table that I know. All I can say is this is the wrong guess. So look at my map again, and I notice I have a link right before g that I haven't used. That doesn't fit the chain rule pattern. So I just broke it down wrong. Well, I can rewrite e to the 2x as e to the x squared. So I can change my function structure. Now g feeds into f, where f is changed to include the square function. So now there's my g leading into f. My f is now 1 over square root 1 minus a square. I know that. That's inverse sine. So this is the right guess. Now that I have my guess set up, here's the method. Set g equal to e to the x, just like we guessed. But this gives me a functions calculus schematic. G is a function of x. X goes in, g comes out, e to the x is the function that takes it. And the derivative connects the differentials. dg e to the x dx. The derivative of e to the x is e to the x. So the method is 2 steps. Step 1, put in your g. This thing you should know. If you don't, it's going on the wrong course. Then plug in your differential. It should be everything else. Now you're at a known antiderivative, and you replace g with what it really is. This method highlights the usefulness of having dx at the end of the integral for the notation. Because when you change variables, you have to change the function value and you have to change the differential. Having the dx set to the end of the integral helps to keep track of how the differential changes when you do a change of variable. Another example is always helpful. Map out the function. Feed it through the linear, the reciprocal, multiply by x. I need to multiply by a function, so that's the function 1 times. Bottom link, that's got to be g prime. 2 times, 1 times, constants we can always adjust. So there's my f, 1 over 1 plus the input. I don't know that antiderivative. It's the wrong guess. I know the antiderivative of a reciprocal, it's natural log. And the derivative of a linear function is the slope. Chain along. That'll work still. So there's my guess. G is 1 plus x squared. dg, the derivative, dx. Substitute in g only. Everything else is going to be taken care of by the differential. X dx has to match with the differential. It's only off by a constant, so I can throw it on the other side. Pull out the constant, and there's my natural log. Substitute back what g is, and there's my answer.